How you doing, Fusion fans? Today we have a very special interview with Dr. Joe Khachan. Joe Khachan is Associate Professor of Physics at the University of Sydney in Australia. We're going to be talking about his career, his work with tokamaks, IEC, and Polywells. So stick around.
My name is Joe Khachan. I work at the University of Sydney. I'm a member of the faculty there in the School of Physics. So that's basically who I am.
When did you first get interested in plasma physics?
It was, well, it's hard to put a date on it, but if I was to put a year on it, it would have been 1992. And the reason I do remember that is because my PhD, which was from the University of New South Wales, which is also in Australia, was not in plasma physics. It was in low temperature solid state physics. And one thing led to another, and my postdoc ended up being in magnetic materials in another Australian university. And in the end, I was just making better transformer cores. And so I didn't see a bigger picture to that. Although the environment there was absolutely fabulous, the people were fabulous. This is a university called University of Wollongong, beautiful campus. The work, when it started, was incredibly challenging to make an instrument to measure 50 micron thick materials of amorphous metals and their magnetic properties. And I found that enormously challenging and therefore enormously satisfying. But when that work was done, the challenge had gone, and I started to wonder what other challenges there are. So I'd be reading books by the book by Francis Chen, Introduction to Plasma Physics. I'd also was reading books about spacecraft propulsion, electric propulsion of spacecraft, and lightning and things like that. And it dawned on me that I actually am interested in plasma physics for whatever reason, and then decided to basically quit my job, which was, it was a long-term job, and it was, as I say, a fantastic environment, but I actually walked out of that job. And then I asked the people at Sydney University, who at the time I knew had a tokamak, a very small one called TORTUS tokamak, and I asked them if I could work on it at no charge to themselves, and to my surprise, they agreed. This guy with a low temperature solid state physics background, they've accepted him as to come and work on plasma physics, which is really odd, but it was the best decision I ever made, and I've never looked back. It was the right thing to do for me.
Can you describe TORTUS?
It was a very small machine. When I came to the university in 1992, I was at the tail end of its life. Shortly thereafter, a few years after, it was decommissioned. But my recollection of it was a major radius of, it would have been less than a meter, and the minor radius, maybe, 30 centimeters or 20 centimeters, very tiny machine. But yet, it could produce confinement times of about 30 milliseconds. It could achieve a plasma temperature of about 300 electron volts. And for its size, that's quite a remarkable achievement. But, it was costly to the school. It was paying for 3 full-time technicians on that machine. And the times were changing such that the school just would not support specific projects out of the main school budget. You'd had to get a grant, for that sort of thing. The machine produced a lot of PhD students doing all sorts of work on that. I did a little bit of work on that, learned something about tokamaks. The head of that group was Professor Rod Cross, who is still in the school, now retired, and he designed and built it. And it was a machine that he used in many ways. One of the ways was to study a kind of plasma wave called an alphane wave. And he wrote a book on that. I think it was one of the first few books on alphane waves. Yeah, so that was TORTUS. And the experiments I took part in were interferometry experiments, far infrared interferometry, to get a mapping of plasma density across the plasma. And that was enjoyable, but I learnt something about plasma. That is, diagnostics are everything. If you do not have diagnostics, you are blind. You do not know what's going on. And theory can help you, but generally doesn't help you very much. And so, because plasmas are inherently very complicated. And so I learned that there are certain practicalities when tokamaks produce a pulse, the ground shakes, and all your optics can shake with them. And then you have to live with that kind of for want of a better word, response function on your instrumentation to try and deconvolve that out. Anyway, so I learned the realities of high-powered plasma physics, and that was decommissioned. But anyway, so that's hopefully in a nutshell the TORTUS tokamak. It was built in 1980. It had a working life of perhaps 15 years, and that would have taken it to 1995, and I became member of the faculty in 1994, but I'd been there 2 years previously working on it and other plasma projects.
After TORTUS shut down, what was your next sort of set of projects? What did you work on next?
Well, in conjunction with the TORTUS, I had a project which wasn't fusion-based, and the reason I liked those projects is because, as I said, I am a low-temperature solid-state physicist, and on top of that, I mostly did quantum mechanical theory of low-temperature solid-state physics, although I did have quite a large experimental bent, if you can say it that way, and the bulk of the work I did was experimental, but the bulk of my publications were theoretical. So it teaches you early on that, both are difficult. Experimental physics and theoretical physics have their own peculiar difficulties. But I have to tell you, having had a foot in both camps, yes, they're both challenging, but you can put out more papers in theory than you can with experimental work. It takes a long time to get decent experimental data. So the project I had in conjunction, so the reason I did these other projects that weren't fusion-based is I needed to learn all I can about experimental and theoretical plasma physics, and I needed to learn it from people that have done this for decades. And the group I was with at the University of Sydney were absolutely fabulous. They still are. They're all retired now, but they're still there at the university. And I learned a lot from them. The project I had in conjunction with a tokamak was what you might call plasma processing. It was a microwave plasma, and you could generate a plasma from using microwaves out of hydrogen and methane, and exotic chemistry happens in the plasma, and if you put a solid surface such as silicon in contact with the plasma, you get deposition of polycrystalline diamond. And diamond, you can grow diamond out of a plasma. So it made the local media here, and the reason was, of course, it's all unfunded, but I was able to get parts, a magnetron that's used in microwave ovens, some downpipe. There was a small vacuum chamber still available from legacy projects. Pumps were lying around, and so myself and a superb technical officer, John Piggott, put that together, and we actually made one of these microwave diamonds, diamond-forming plasmas, and we published the paper, and then there was local media interest, and I got my first experience with media hungry for, probably a bit of a disparaging word, for a furry animal story. Those stories they put at the end of a news item about a cute animal that, I don't know, does something, has a limp or something, or is just cute for some reason. I was the furry animal story. And after that, I didn't feel too good about that. And then it all disappeared. And I thought, wow, they weren't really interested. It was just a quirky story, someone making diamonds out of microwaves. But the value of that was quite a few students came out of that project. I learned a great deal about plasmas, modeling plasmas, all the ins and outs and the quirkiness of plasma physics, experimental plasma physics, that is. It was a great learning experience.
When did you start work on space thrusters?
The thruster was a consequence of IEC. I started doing, after the tokamak was decommissioned, I still had my microwave plasma project. And in 1998, I was dissatisfied with the microwave plasma because that's not why I came to Sydney University. They're interesting, you can do useful stuff with them, but I really was after the energy challenge. Can you make an energy device out of a plasma? Let me add at this point, I'm not, in a sense, altruistic in that sense. I never thought about, I'd like to make a device that benefit humanity. I have to be honest, that never even crossed my mind. There was a technical challenge about trying to make energy out of a device, and that is the interesting bit for me. And so I started to think, how do I get into fusion now that the tokamak's gone? And I thought about the sun and how the sun makes its energy. And if you think about the sun, it's basically a centralized force, the gravitational force, that draws matter into it. And it accelerates matter and heats it. And because there's lots of space around it, that matter can't go anyplace. It just is stuck there. And the sun can heat matter and trap it or confine it. Very high densities. And at some point, the matter ignites in a fusion reaction, and that's the sun. So I thought, how can I do that? And that's when I thought of the idea of IEC, except IEC being Inertial Electrostatic Confinement, but I didn't know it was called that. I remember telling our head of a department, Rod Cross, how about we make a centralized, not gravitational force, but electrostatic force that draws ions into it and heats them and confines them? Why is it that we had tokamaks and we didn't have an electrostatic form of confinement? And he said to me something surprising, thinking I had a really original idea. He said, oh, I think that's been done. It's a guy called Robert Hirsch, and here's a book about him. And I just couldn't believe that somebody had thought of this. Anyway, so I go away and read the book, and Robert Hirsch is in there, and there's the story about Hirsch making this device and putting it on a trolley, and, you know, people who are into IEC know the story, so I won't regale it. But I was lucky in 2000 to spend some time with Professor George Miley and Dr. Hirsch. We had dinner, and I asked him, did he really do that? Did he put the IEC machine on a trolley? He said, yeah, it was a dining cart. He put it on a dining cart.
I haven't heard that story.
Oh, you haven't?
I haven't. No, I haven't.
Oh. Excuse me.
He put this IEC machine on a dining cart. You know, it had I think 6 electron guns, if I remember correctly, and the pumps and everything was on this dining cart. And he walked into, I think it was the US Atomic Energy Commission or something like that. And it was a meeting for them, and to show a committee there that, here, I've got a really tiny device and it produces fusion. Can you fund me, please? And he said the way they were impressed, they thought that, you know, they couldn't believe such a small thing can produce fusion. They thought it has to be very large. And I think he told me at the time that the way they talked about it and the way they looked at him and told him in not so many words that they weren't going to fund it, and they didn't fund it. And that's the story. But anyway, so before I met them in 1998, I started, after Rod Cross had given me the book, and I wish I could remember the title of that book, but it had a chapter about Robert Hirsch. And I started to make my first grid and use existing vacuum chambers, as I had access to try and make an IEC machine. And so the first thing I did, being now, I guess, a diagnostician, a plasma diagnostician, because I'm now trained by the group who are all into diagnostics. And the first thing I did was aim an optical emission spectrometer at the discharge. And to my surprise, in the 5 decades of IEC history, no one aimed a spectrometer at the light. There's light coming out of this thing, just point a spectrometer to it, because it will tell you a lot. And it was amazing what I found. Sorry, I'll make the point here that I'm still aware of the question of how did I get into thrusters, but I need to explain why I got into thrusters, and it was because of the spectroscopy I did on IEC and incredible things that you see when you point a spectrometer. The first thing you notice is the energies of the ions are extremely high, and the way you notice them is from Doppler spectroscopy. And if someone's listening to this and is familiar with Doppler spectroscopy, they'll say, oh, but you're doing spectroscopy on hydrogen, which has no electron and therefore emits no light. And that's true. The way you see the light is when the ion picks up an electron from the background gas. This is a process called charge exchange. When it picks up an electron from the background gas, the electron around the now neutral ion, neutral but high energy ion, is in an excited state. It decays, emits light. That light can be Doppler shifted depending on the velocity of that ion. And you see something really interesting. The first thing you see is that a deuterium ion is a minor component to this plasma. There's deuterium. So I mostly dealt with hydrogen in the initial stages. I'll say hydrogen. Deuterium is an isotope of hydrogen. They behave in the same way. Since then, I've done a lot of spectroscopy on deuterium. But what you see is hydrogen molecules. You see an H3 molecule, that is 3 hydrogen molecules clumped together, as atoms clumped together. You see H2 molecules, high energy ones. And then a small component is H, or hydrogen. And so now you realize that, oh, I may be putting in, say, 30 kilo electron volts. But the large component of that plasma is, a lot of the time, it's H3, or D3 if you like. You have to divide the energy you give that molecule by 3. So instead of 30 keV of energy, you're giving each atom 10 keV. You're wasting energy. So the first thing you realize is you're throwing energy out just because of the nature of the plasma. And you have to think, well, if I'm going to increase the fusion output, I've got to make a fully ionized plasma that is get rid of all the molecules. And that's difficult to do. You have to put in a lot of energy. So that's the first thing I found out, that from charge exchange, you see the behavior of the ions. But the process of charge exchange, the fact that I can see a lot of it happening, tells you this device cannot work as an energy device in its current form. If you have a gas and you produce this nice glowing discharge, the fact that you see a glow from charge exchange, it's all over. Because charge exchange means you have neutral energetic particles that leave the system. You have a big energy leak. If you want to make this device as an energy device, again, no background gas and a fully ionized plasma. And that's from day one. You know, you aim a spectrometer and then you see, oh, it can't work as an energy device in this form. So yes, but of course, I can tell you that it can work as an energy device, provided you got rid of the background gas. And of course, and by the way, I don't want to put anyone's work down. There's a lot of superb work that's gone on, but even the lowest pressure experiments I've seen still have a substantial amount of background gas. Even if you're operating at the microtorr region, there's still a lot of gas and a lot of charge exchange that occurs. You really do need a fully ionized plasma. As the tokamak people do. They fully ionize the plasma in the core of the tokamak. Otherwise, it's all over. So those thoughts I got just by aiming a spectrometer. It's that simple. I promise you, there is nothing difficult about aiming a spectrometer. A lens and a spectrometer is all you need. And you'll see that. And I wrote some of this work up, and there was students working with me at the time, and students are absolutely fantastic. They'll have ideas that I don't, and then we chase them together. And one student, this was now, I think in the 2000s, he said something really odd to me. I said, look, let's do spectroscopy. I've done all this before, but I've gotten the chemistry, I've gotten the energies, and all this sort of stuff. Let's just do more spectroscopy. I don't know where this will go, but let's. And he was doing his PhD. And he comes in one day and he says, you know the picture of IEC where ions are coming towards the center of the device and fusing? He says he didn't see that. He sees ions heading away from the center, accelerating away from the center. And I thought that, I said, let's go down to the experiment and check it, because you clearly have your optics wrong. They're supposed to come in. That's what the theory says. They come in. How can they not come in? And lo and behold, when you start to do spatially resolved Doppler spectroscopy, in that, that star mode, where you get these nice star-looking discharge. Yeah, all directions. And even when you go to lower pressures, what I'm about to say still applies. What you see, and you see some ions heading in, but the bulk of the ions, the higher density of the ions, they start within the cathode, within that grid that people do at the center. And they accelerate out, and they charge exchange, and they leave as neutrals. And this is a bad thing. This is not a confinement device. It's an anti-confinement device. And the reason is that there are many reasons, and which I'm still pursuing to this day. In fact, I'm writing a few papers on that. This is not a fully ionized device. It's a discharge device. Now, when plasma physicists talk about discharge, they mean the effects on the plasma have a substantial component upon them from the background gas. That is, the reactions with the background gas tends to dominate. And so this is a discharge device. It is not what you call a plasma device which has fully ionized. That has a different behavior than a discharge device. And so there it was. The idea was, well, forget it, you know. If you want this thing to operate as a discharge device, as an energy device in this discharge mode, you're dreaming. It's not going to happen. And so it was interesting because it does produce fusion, a lot of it, but it wasn't going to be an energy device. But what came out of that was, oh, this thing throws out neutral particles at really high energies. And so I was working with another student and I was telling him about our findings and that it's throwing out neutral particles. It so happened that student was also an aerospace major. And he says, oh, do you think you can make it throw them out in one direction? I said, I don't know. Maybe it's a matter of shaping the cathode, which is the grid. And we tried and we could. We could make it throw them out in one direction. And he said, I think we can make a thruster out of this. And I didn't know much about thrusters. And to me it was, well, why would you? There's lots of thrusters around. You just throw mass out and things move in the opposite direction. And he said, no, in electric propulsion of thrusters, which is, if you're into long-term space travel, you want electric propulsion because you use very little fuel, you have very high exhaust velocities, you can get to very high speeds. And he says, no, in electric propulsion, what they do is they throw out ions. But if you only throw out ions, your spacecraft will charge up to a negative charge and then it will draw the ions back in. You get no thrust. You have to throw out electrons with the ions and so neutralize them and so keep throwing out electrons. And those electron guns can fail on you. And so what we had here was a self-neutralizing thruster from charge exchange. And we tried to get it patented, and we called it the charge exchange thruster, CXT. Now they all have to have an acronym. And then we went to the university and they said, oh, that looks like a niche market. Don't worry about it. Let's just go publish it. Not worth patenting. And that's where it sat in 2007, and I left it alone, thinking, well, yeah, that was a nice, interesting experiment. And that's how we got to the charge exchange thruster out of the IAC.
After that, you started work on the Polywell. Can you talk about how you started on that and just lay out the work that you did in that? I know it's a lot.
Yes.
So keep in mind that the work on the Polywell was the IEC gridded work was still going, and it's still going. I actually still have it going because later I can tell you some interesting things about it. But the work on the Polywell, there was I knew it was going on because when I visited Professor Miley in 2000 in Illinois, I spent my sabbatical there, and it was the best sabbatical that anyone could ever spend because I met key players in the IEC fusion community. The welcoming nature and the warm nature of Professor Miley was outstanding, and I learned a great deal by being there. And so I knew about Bassard's work, but I never got to meet Dr. Bassard. But I knew of his work from Professor Miley. And I came back and continued work on gridded IEC. And there was, I'm not much for reading blogs, but someone from the blogging, I forget which one, the Polywell blog or, I'm not much into the blogs, but one of the blog, what do you call them, administrators, or I'm not sure what the term is. He's an Australian guy and contacted me and said, why don't you do polywells? And my understanding of them was, you need high magnetic fields and there's a lot of technical infrastructure to do. And I didn't think I had the money or the space, so I didn't do it immediately, but it stayed in my mind because when you know what you know about the gridded IEC system, that under these discharge conditions, it can't work, not just from charge exchange losses, but you can see the grid become incandescent. That's a lot of loss of ions striking that grid.
So it glows like a light bulb.
And it glows like a light bulb.
With all the plasma's bagging into it.
Absolutely. So I started to think if you can just replace, as the Polywell wants to do, replace that grid with something that isn't metal, something which wouldn't put a dead stop to ions, which is an electron cloud, which is what the Polywell tries to do. And I think it's a great idea. Because from the thruster work, I learned there is something similar to the idea of the Polywell in thrusters. There's a thruster, a very, very successful thruster called the Hall effect thruster. And what that tries to do is create what's called a virtual cathode. That is a cloud of electrons that extract ions from a discharge within the thruster. It's not a physical grid, so it can't erode away as previous thrusters could. They could erode the grid away. So they trap in a magnetic field, in an E cross B field as it were, electrons, and they draw in the ions and accelerate them. And so the polywell is a version of that. A polywell is trap electrons in a centralized region, and that's your attractive potential to ions. And now you don't have the grid problem. But again, if you want to do that, it better be fully ionized. Otherwise, you're going to have charge exchange killing your whole process. You're not going to win the energy game. Because charge exchange probabilities or cross-sections are at least 8 orders of magnitude greater than fusion cross-sections. You're not going to win. You're just not going to win. You have to get rid of the background gas. It must be a fully ionized plasma. And so that's how, a blogger came to see me. And that's how I sort of started to think about it. And then students came to see me wanting to do PhDs because I am the only person doing IEC in Australia. And then that's when I said to the student, look, there's this idea called the Polywell, which is trademark name of Dr. Bassard. And perhaps I don't have the money. I've never been funded for fusion work. I don't have the money, but maybe we can do it on the cheap. And we made a tiny little Polywell, small electron guns. But it was incredibly revealing. It's so revealing that I'm glad we did it. And the student was called Matt Carr, who now works on JET, the Joint European Torus. So that's how I got interested in Polywell, and that's how work got underway by a student coming to see me wanting to do something on IEC fusion.
You mentioned earlier that you haven't received funding for fusion. In a perfect world, what kind of resources would you need to do the kind of proper job, proper work that is needed?
Yeah, let me preface that to say that in the last couple of years, I have been funded for fusion work, for IEC fusion work, enough to pay the salary of a postdoc. That's the level of funding that was at for 1.5 years, and that's more than I've ever got. So in an ideal world, what would I want? IEC, even Polywell fusion, is relatively cheap to implement. The hardware you need is really not that expensive. Even someone as underfunded as me can tell you it's not that expensive. You can do it on the cheap. The biggest resource you really need are people, skilled people, and that's where the money will go. So in an ideal world, what would you want? Well, from my point of view, proof of concept should be mostly over in, I know this sounds ridiculous to say, but you should get a really good idea if this thing's going to work, especially an IC machine, which is small and things happen quickly with that. You should get an idea in 5 years, if you are properly funded. Not the way I've been funded, which was basically in the past zero funding.
So we're talking on the order of $1 million a year, $10 million, that sort of thing.
$1 million a year would pay you the salary. You want an electronics technician, a mechanical technician. You want 3 experimental plasma physicists at least. If you have extra money, a theorist would help. And you want to fund these people for at least 5 years. Preferably 10, but 5 years is, I think, a realistic funding timescale. And so if you add all that up, you probably are looking at $1 million a year, $2 million as a luxury, but $1 million a year would get you through. In 5 years, you should have an idea whether this device is a goer or not a goer. And you can imagine all the things you have to do. You know, as I say, the first thing you have to do is get rid of that background gas. You must have a fully ionized plasma, which now means you might need to have microwave heating of the plasma to make it a fully ionized plasma. So yeah, the resources are people. Of course you need space and equipment, but they're kind of one-off costs other than maintenance costs. I don't view that, for IEC and Polywell fusion, I don't view that as the major cost. You know, a reasonably large vacuum chamber and the pumps and whatever might set you back $100,000, but that's a one-off cost. A person, in Australia at least, per year would cost you more than that. So it's people. People is what you need. They're your biggest resource. And enthusiasm. You don't want someone to treat this as a job. You know, I'll just move on to my next job. They really have to have a hunger for making this thing work. And because with hunger comes, and passion for it comes ideas. And this is what you need. So yeah, so that's the resource. People.
For the listeners who don't know, you've published, I think, 4 or 5 papers on the Polywell, and
I think so, something like that. Yeah, probably maybe 5. There's been other papers that are related to the Polywell, except they never used the name Polywell. For example, there was one project where we wanted to find out, what if you take away the magnetic fields of the Polywell? What if you just had the grid that... So just for listeners, the Polywell is you draw in electrons to a centralized place, and those electrons draw in the ions. As we've said before, the electrons act like the grid, except you don't lose energy to them. You don't lose much energy to them. And so we had a project where we use a normal IEC grid, but this time it has positive polarity. So now you draw in electrons, and you form your electron cloud or virtual cathode within it. What happens? What happens if I have the freedom of being able to draw large amounts of electron current to form a really deep potential well inside? Is this a stable device? That's the first thing you want to know. Is it going to suffer from instability problems as tokamaks do? And you start cranking up the current, and I think we got to 20 kilovolts, 1 kiloamp of electron current. It's huge. And at that point, you start to notice an instability. We think it's something called a Boonman instability. It's basically like an oscillating plasma sphere, but it doesn't have to be. It can be like little eddies of electrons, but it's not fatal. It's a good instability. Those instabilities can accelerate ions. So it's not a bad instability, but it's an instability there when you get to really high electron currents, which shows you that in the limit, if you have say you had a Polywell device that was operating as a baseload power plant, let's just dream a little bit, and you're drawing in kiloamps of electron current to form your virtual cathode, then you could start to notice these instabilities, but they're not fatal. So we've had publications like that, but they weren't labeled as Polywell. So that was a PhD project. But yeah, on the Polywell, I think you're right, there's probably 5 publications. There's still more to come, by the way. I'm currently working on a couple. Yeah, so there's a lot more to come.
Is there anything you're currently working on that you want to promote, discuss, something that you think people should know that you're working on?
Yes. As I say, we're about to put out certain papers. The papers I'm currently writing are, again, work that was done as a PhD about how a Polywell device would scale. For example, as you know, we've started with small scale largely because of lack of funding, but also you need to start there because it's a manageable plasma. You don't need to put a lot of power in. We did work to find out, how do the potential wells that these virtual cathodes produce, how do they scale with the geometry of the Polywell, the magnetic fields, the electron currents? How does the confinement time of the electrons? What is the leakage rate? So all that work was done. And some of it's been published from Matt Carr's work. I think a lot of it is still in his thesis. Maybe we should have written more up, but it's in his thesis nonetheless. So there was work that we'll put out about scaling, Polywell scaling. If you want to crank this thing up, how must you make it? So that's currently the work that's in progress. There's 3 separate projects in progress. One of them is regarding traditional gridded IEC, where the grid is actually negative and it draws in ions, and we've discussed the problems with that. But the question we asked was, what if you had a grid that was magnetically shielded? So that's not a new idea. It's mentioned in previous publications by other people, such as Thomas Dolan. And so we made such a device, and the grid, it's quite an undertaking to make such a device, because the grid has to be at, say, 30 kilovolts or 50 kilovolts, but there's a magnetic field coil that's inside this hollow grid, and that has to be essentially a ground potential. And so you could get severe arcing, and so it was quite an undertaking to electrically insulate the two. Nevertheless, we got there. We can produce a magnetic field of a few Tesla around the grid, and the magnetic field is conformal with the circular cross section. That is, so the grid can be shielded from the ions. And we haven't published this work. It's not complete because there were other issues with the device, and that has to wait for another year or a few years from now to see the light of day. But one thing you can say, and it becomes immediately obvious, as you crank up that field. Now, for people that do IEC, as they crank up the voltage, they see the discharge current rise. Well, the same thing happens with this device. If you crank up the voltage, the discharge current rise, then you start to crank up the magnetic field, and the discharge current starts to fall. And yet, it's the same density plasma. So there's a bit of ion trapping going on, a bit of circulating current.
It's a balancing of two effects.
Absolutely. And so now you start to get the idea, oh, I can make the grid transparent to the plasma. The grid doesn't have to see the plasma. And now, if I've trapped my ions, I could have a shot at making an energy device. And so we were quite elated in finding out that the shielded grid does amazing things. But I come back to the same point. There's a lot of background gas, and there was problems with discharge physics. And that has to be eliminated. That's why I say we can't do it now. We do not have the resources such as, RF heating and so forth, in order to make a fully ionized plasma. The other work that's going on is the Polywell work. And now this work is, because of our previous work, there was quite a considerable leakage of electrons from the Polywell. And so we thought, what if we made a device, a Polywell device, where the magnetic fields are in the many Tesla? Like, you'd really try and trap them inside. And so this is our current project on the Polywell, a couple of Tesla around those coils. And already you see wonderful things. You see the electrons within the Polywell start to take on the cusp shape of the fields. Sorry to your general listeners, but how do we describe it? It's a form of star structure where the center of it is zero magnetic field, and as you move away from the center, the magnetic field increases. But you see that shape. You see the electrons trapped in that shape. And it's absolutely wonderful, especially when you take slow motion video of it and you see that star shape, that cusp shape develop. But the reason we see the shape is because there's background gas, and those electrons are exciting the background gas. So in truth, we shouldn't see anything. It should be dark in there if it was just a proper fusion device. Now, it should be dark in the visible range. Probably in the X-ray range it won't be. So that's a project that's going on at the moment. The third project is to do with a nutty blue sky idea, to do with normal gridded IEC. For a number of years, we've noticed something odd about IEC, gridded IEC devices, the star mode. And as you go to lower pressures, that star mode is in there, but to be honest, the physics is there. Let me just say, just in case there are people that do IEC that are listening to this blog, this webcast, that the star mode, the stars that you see are not, the major composition of those channels are electrons. They're electrons heading away from the grid and exciting the background gas. That doesn't mean there's ions heading in, although ions do head in. But it's electrons, and there was a publication that we put out. Again, you may not find it under a normal IEC search, but there was a publication we put out where we put essentially two magnetic field coils, a so-called Helmholtz pair, across one of these channels. And by applying a magnetic field, you can bend one of those channels. And the bending angle tells you the energies and the species. And the energy and the species are electrons, and the energies are the energies of the potentials you apply to the grid. That's the bulk of those channels. The ions heading in, the charge exchange, is a small component of that glow. And so there's been a lot of work done. But one thing we did notice was, because we played around with a lot of IEC grids, and one thing you notice is if you change the shape of that grid, if you change the material of that grid, fusion rates change. And at first I thought it was my neutron detector. I thought, oh, it must be inconsistent because of low neutron count. So I got more sensitive detectors. And nope, the effect is real. They change. And so I started to look into, well, why, this may not be an energy device, but it's an interesting question, and therefore, because it's interesting, it's got to be pursued. And so it turns out that remarkable things happen. And probably I shouldn't preempt our publication because there are extraordinary things that happen. I probably won't mention the materials. Some materials produce an order of magnitude higher fusion rate than stainless steel, for example. Some materials, the electrons, from spectroscopy, you can see ions heading towards a material and ions bouncing off materials. Except those materials that have the highest fusion rates, you see very little bouncing off them, as if the ions are being embedded inside them and somehow fusing there. And when you look into that, you find out there's a whole body of work not connected with IEC. And it's about when ions embed in a crystal lattice, you get the density of electron states inside that lattice going around the embedded ion, and they have the effect of what's called Coulomb screening. So if another ion is coming in, it doesn't see that ion that's embedded in the material because it's been shielded by electrons. And so it's not easily repelled until it's too late, when it goes into that electron cloud and then sees the ion, but then it's too late. So that has the effect of increasing the fusion probability or cross-section. And so we're looking into that. And so keep in mind that whenever I've told people this, they say, oh, isn't that cold fusion because it's something to do with materials? No, it's still pretty much hot fusion. It's just you're making a use of a quirky materials effect. Now, you start to play around with ideas. That is, you say, well, how much does the fusion rate increase from this embedded electron cloud? And it increased substantially, but not enough to give you an energy gain in fusion. Then you ask the question, well, how much shielding do I need to get an energy gain? And it turns out 2 or 3 times more. Doesn't seem to be a lot. And so, but then what material do you choose? And now I have one project that's trying to do this experimentally, and one project to do it with theory called density functional theory, which can simulate the electronic behavior of crystal lattices, and to see if you can make a material to achieve 2 or 3 times Coulomb screening. So that's the third project. So these are the 3 current projects. Hopefully in years to come I'll be able to publish on them.
What do you think we need to be doing better to facilitate and accelerate fusion power development? In a perfect world, what would you want to see?
You see a lot of startups and you think, oh, that's the way to go. Startups, money, things will happen. And I agree that is a way to go, because governments can fund fusion, but there's a lot of politics and you got to apply for grants, and some grants are incredibly competitive and it's hard to get. So startups are a really good way to go. The problem with startups is people want to see a return on their investment. And I think you can't view, yes, you need to see a return on your investment, but it mustn't be like a 5 or a 10-year time scale. Fusion is for the long term. What must happen is, yes, your startup may have employed, I don't know, a few hundred people, maybe there are tens of people that are scientists in there. Believe it or not, that is not enough. It's not enough to speed up the science. You need thousands, and the way you get thousands of people is you have publication with peer review. That means you must be able to publish and be assessed by your peers. And venture capitalists hate that because they say, oh, you're losing IP, you're losing intellectual property. And I don't think you are. Because anyone that's made a machine and published on it, you know there's a lot of little things you had to invent to make the physics happen, which you never published on. There's intellectual property there that you can patent. So there must be open peer review publications. And I think that would speed up fusion enormously. But for a large part, some companies do publish, not everything. For a large part, they are a closed shop. And so from my point of view, and I'm probably a guy that no one would want to invest in now, you have to have open peer-reviewed publications. That's how you speed things up in an ideal world.
So you're coming down on the side of information openness versus information
Absolutely.
Security and hiding.
Absolutely.
Yeah. Okay. So this is my last question. Is there anything else that you want to talk about that we didn't discuss?
Oh, I'll put one point in, that you look at some blogs and it's as if, it's true, there's electron leakage from the Polywell, but it's not the death knell. If you think about it, if electrons leak out of the Polywell, they put energy back into the electrostatic field. As they leave, they're attracted back. That is, their kinetic energy turns into electrostatic potential energy. So electrons leaking out doesn't mean you've lost energy. You've lost an electron, but you haven't necessarily lost a lot of energy. That's why in tokamaks, they talk about energy confinement, not necessarily particle confinement. You can lose particles, but not necessarily lose energy. Of course, with things like charge exchange, you lose particles and therefore energy. So yes, you have to narrow down. You have to narrow down the loss areas of the polywell. But even if you lose a little bit of electrons, it's not necessarily a tragic thing. You get that energy back in the electrostatic potential field. And you don't see anyone talking about that. So I guess that's probably the most important point to add. But otherwise, that's probably enough on the polywell. And I just wanted to add, I think I speak for many of us who work in this field, that we generally are very bad at informing people out there who want to know what we do. And we're so ever grateful for you, Matt, for making such an effort.
All right. Well, thank you very much, Dr. Khachan. And